Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about transformer under no load condition and load condition, ideal transformer on no load, practical transformer on no load, and practical transformer on load condition. That phasor diagram we will discuss. So first, before going to explain this load condition and no load condition, I would like to explain ideal transformer and practical transformer. What is the difference between ideal transformer and practical transformer? So ideal transformer is an imaginary transformer which does not have any loss, and it means no core loss, no copper loss, and any other losses in the transformer. Efficiency of transformer is considered as a 100%. Now here, first of all, the winding resistance of transformer is 0. Primary winding resistance and secondary winding resistance. If winding resistance is 0 means I square R losses are 0. Primary winding resistance and secondary winding primary winding losses and secondary winding copper losses are 0, and losses are 0 means efficiency is 100%. Efficiency is 100%. And next condition, permeability. Permeability is very infinite permeability. Permeability is infinity. So these are the four properties. First one is winding resistance is 0. I square R losses, copper losses are 0, and efficiency is 100%. And next, permeability is infinity. Another next one, this is first, second, third, and fourth one is permeability, and fifth, flux linking is 100% and leakage flux is 0%. So now here in the ideal transformer is an imaginary transformer which does not have any loss. So any loss this one, and means no copper losses and no iron losses, and efficiency is 100%. This is transformer. If you talk about the practical transformer, as we said that here ideal transformer, there are no copper losses, but here in this there are some losses. That losses in the core losses, hysteresis losses, and eddy current losses in the, and also some copper loss. There may be a resistance, copper losses are present, iron losses and copper losses are present in the practical transformer. So now I will discuss first ideal transformer on no load and practical transformer on no load and practical transformer on load condition. I will explain now. Ideal transformer under no load condition. Ideal transformer under no load condition means here, now here ideal transformer under no load condition means there is no load. Here there is no load means it is open circuit. It is open circuit. See this diagram. So here V1 is a supply voltage, and if you give the V1 voltage to this primary winding, and I1 current flows in this, and here induced EMF will be developed in the secondary winding E2 in this, and this is E1. Now here, according to the Faraday's law of electromagnetic induction, E1 and mutual inductance concept, E1 and E2 will be developed in the primary and secondary respectively. Now here secondary winding current is 0 because it is an open circuit. This is the circuit condition for ideal transformer. Now here this I1 current set ups the flux, means this current is main cause to produce the flux here. So because of this reason, this I1 current is known as a IM, magnetizing component of no load current, because here there is no load, and here it is, this current is responsible for this main flux which is in the core. So now here this current is known as a I1 is known as a IM, that means magnetizing component of no load current. Magnetizing component of no load current. Now here in this, it is ideal transformer. In the ideal transformer, resistance of R1, primary winding resistance R1 and R2 is 0 in the ideal transformer. Now here R1 and R2, resistance is 0 means this impedance Z equals to R plus JX. So now here this primary winding resistance R1, X1, J1. If resistance is 0 means this is 0 means it is purely inductive, pure reactance. Z1 equals to JX1. So it is pure inductive load, pure inductive coil. So in case of pure inductive case, voltage and current. So current lags voltage by 90 degrees. This we know this. So here if you rotate in anticlockwise in this way, so this is the current and this one is the voltage. Is it clear? So now here this is 90 degrees. So current lags voltage by 90 degrees. So this is the IM and I1 is same because it is a no magnetizing component of no load current magnetizing, which is responsible for flux which is produced in the core. Now here this is V1 and this one is I1 or IM. Now here IM set up the flux. Here this IM set up the flux phi. So now here this is the IM or I1. So this one is known as a phi. So it set up the flux means this flux vector is in phase with this one and this one is the V1. Now according to the Faraday's law of electromagnetic induction, and this flux is directly proportional to the d phi by dt, and induced EMF will be developed in the primary winding and secondary winding. Now here this primary winding and secondary winding magnitudes are depending on the number of turns in the primary winding and number of turns in the secondary winding. Now here what will happen? Now here according to the Lenz law. So according what is Lenz law? So the induced EMF opposes the cause producing it, which is the supply voltage V1. So now here it will opposes E1 and E2 opposes, according to the Lenz law, E1 and E2 opposes the cause producing it, which is the V1, supply voltage V1. These two are E1 and E2. So now here E1 and E2 magnitude is depending on the number of turns in the primary and secondary. So this is the vector diagram for transformer under no load condition. Now here this magnetizing current, and take flux as a reference. Flux is a constant flux device. So now here I1 or IM is in phase with this one, and V1 and V1. V1 leads IM by 90 degrees or IM lags voltage by 90 degrees, and here V1 and E1 are completely opposite in antiphase, and this one E2 also is opposite to this V1 according to the Lenz law. This is the vector diagram for transformer under no load condition. Now here second case, this is the diagram. So if you see this diagram, same diagram, I mu means here, I mu same diagram here, V1 phi. I mu means here you can represent this magnetizing current with I mu also, and this is E1 and E2. So this is the vector diagram for transformer under no load condition. Next, transformer under practical transformer. So practical transformer, in the practical transformer there are iron losses and copper losses. When iron losses are present means in the transformer, here this is the transformer. Iron losses means eddy current losses plus hysteresis losses. Eddy current loss, which causes the eddy current losses and hysteresis loss. That means core losses or iron losses when alternating current flows in the magnetic core. So now here these are the copper losses. So these losses must be minimum while designing this transformer. Any transformer, while designing the transformer, these losses must be minimum. So this iron losses, this eddy current losses can be reduced by laminated core construction. Here this hysteresis losses can be reduced. The material if you use that high grade silicon steel material, then hysteresis losses can be, we can minimize. And apart from this iron losses and eddy current losses and hysteresis losses, there may be some copper losses are present. Copper losses means here, because of this winding resistance I1 square R1 and I2 square R1. So here it is a open circuit, means there is no current, there is a resistance but there is no current in the secondary winding. I2 current is 0 open because of open circuit, so we can neglect this one. So now some amount of primary copper losses also present in the winding. So now here these are the iron losses and these are the only primary copper losses are present in the transformer. Now here this no load current I1 is we can call it as I0. So no load current of primary, if you give supply to this primary winding, some current flows when there is no load, and this current is known as I1 is known as the I0 is here. This I0 is divided into two parts, I mu or Im we can call it as, and IW or IC. I mu and Im is a magnetizing current. Magnetizing current. This one is the core loss current. Core loss current or watt full current. Watt full component. And this one is a watt less component or power component. Power component or magnetizing component or watt less component or reactive component. Reactive component. We can call it as, here this one is the active component. What are the names for this current? So first, magnetizing component of no load current, watt full watt less component of no load current, and reactive component of no load current, and this this one core loss component of no load current, and core watt full component of no load current, and power component of no load current, and active component of no load current. So here this one is represented with I mu or Im, and this one is represented with IW or IC. Now here if you draw the graph, this is the, as we discussed in the previous ideal transformer phi as a ideal phi as a reference. This is the I mu or Im. This one is a V1, and this one is a E1, and this one is a E2. Now here this I1 is I0 is divided into two parts. So this is a IC and IW. This one IC or IW. So now if you draw the graph here, so this one here, this one, this is the graph here. See this diagram. Here this is the no load component of current here. This is the no load component of power factor cos phi, IW or IC, and this I mu, and this one E1 and E2. Now if you write the formulas for this one here, first one is here I mu, from this vector diagram, I mu equals to Im equals to I0 sin phi naught, and IW equals to I0 cos phi naught, and I0 equals to vector summation, and this one plus this one, I0 equals to IW plus I mu. So this is the vector summation, I0 equals to IW square plus I mu square. So this one square root under. So this is vector summation. Now here, so here this IW is in phase with V1, and I mu is lags voltage V1 by 90 degrees. This one because uh, it is purely inductive. Purely inductive. Now here this I mu is responsible for this main flux phi. It is in phase with phi 1, and this V1 is always opposite to the E1 and V1. So now here if you write the power losses W naught equals to V1 I naught and cos phi naught. So this is the formula. Now here copper losses. These copper losses are very less. These copper losses are very less. Under no load condition, this I1 current is very less. So this current is very less, means this losses 3 to 5% of full load current of transformer, full load current. So these losses are negligible. Only we have only copper losses. So this losses, this power loss can be called as a constant loss or core loss or iron losses. Now here next one, practical transformer under load condition. Practical transformer under load condition means here when you connect the load, here this is important, when you connect the load, current flows in the secondary winding. It circulates the current, that current is I2. When you give the supply voltage V1 to the transformer primary winding, current flows in the primary winding, that current is I1, and this I1 current set up the flux phi that is links with the transformer core which circulates in the transformer phi. So this is the phi. So let me change the color over here. This is the phi. This is the phi. And next here this phi is links with the transformer primary winding and secondary winding according to the Faraday's law of electromagnetic induction and mutual inductance concept. Induced EMF will be developed in the primary winding and secondary winding depending on the number of turns and number of turns in the primary and secondary respectively. This is E2. And when you connect the load and current flows in the secondary winding, E2 it circulates. So now this magnitude of current is magnitude and phase is depending on the load condition only. Here this load may be resistive load or inductive load or capacitive load. So this load may be resistive load, inductive load or capacitive load. Now here if it is resistive load, voltage and current, this V2 voltage and I2 voltage both are is in phase. If it is inductive load, so current lags voltage by 90 degrees. And if it is capacitive load, current leads voltage by 90 degrees. These are the vector diagrams. So first, if load is resistive case, voltage and current both are in phase. If it is inductive case, current lags voltage by 90 degrees. This is V2 and this is I2. And if it is current capacitive load, current leads voltage by 90 degrees. Now here what will happen? Now here this I2. So now here let me change the color over here. Now this I2. Here we have I2 and I2. There exist I2 and N2. So the ampere turns, MMF, there exists a MMF. In the secondary there exists a MMF, that is ampere turns into I2. So which is because of this secondary current, secondary flux, it sets up the flux. Phi 2 current sets up the flux. So because of this load, when you connect the load, current flows in this current, low secondary current sets up the flux, and this flux, because of this flux, MMF exists in the secondary winding, and this secondary winding there may be a flux. That flux is phi 2 here. This flux is opposes the main flux. This phi 2 flux opposes the main flux phi, which is produced by this magnetizing component of no load current in the core. And next, this phi 2 flux, this because of this N2I2 MMF is known as a demagnetizing ampere turns. We can call it as this N2I2 demagnetizing ampere turns. Now here this phi 2 is always opposes this phi, and if it opposes the phi, means this phi reduces in the here, this phi reduces here, this phi is reduces this main flux reduces means here E1 and E2 are reduces. E1 and E2 are reduces according to the Faraday's law of electromagnetic induction. E is directly proportional to the d phi by dt. Now E1 is reduces means here V1 minus E1 will increases here. E1 minus V1 increases means there may be extra current. It draws extra current from the supply here. It draws extra current supply here. So that additional current, extra current from the primary is known as a load component of primary current, that is I2 dash. That is completely opposite to the I2. These two are both are completely opposite. And next, this I2 dash set up the flux phi 2 dash. This I2 dash set up the phi 2 dash, and this phi 2 dash flux opposes this phi 2 flux. This phi 2 dash opposes the phi 2 flux and helps to the phi flux. It is opposite to this one, and it helps to this main flux, which is produced by magnetizing component of current. This phi 2 flux is produced because of this load only, and here this phi 2 flux neutralizes this phi 2, and the phi 2 flux helps this one. And next, another thing, there exists a N1 and I2 dash. This N1 I2 dash neutralizes this one, and here there is a N2 I1 dash N1 I1 dash equals to N2 I2. This is important. This neutralizes this primary MMF is neutralizes this secondary MMF. Now here it helps. So at any load condition, so it reduces, it neutralizes phi. There is only phi, and next here phi 2 flux and plus phi flux and minus phi 2 flux. So now here initially there is a phi flux, and because of load component phi 2 flux, and because of this there may be additional current. This neutralizes this phi 2 flux and it helps to the phi flux. This is the scenario for the practical transformer under load condition. If you draw the vector diagrams for this one here, so first one, if it is a resistive load, so see the diagram. If it is the resistive load and E2 and V2, so this one is V1 and this E2 and V2, these two is in phase here, and remaining circuit is as it is. So only the difference is here. So let me change the color over here, red color. And next here, in this case, so first here phi 2 flux, this is the I mu, and this is the IW, and there is a I naught and I2 dash. I naught plus I2 dash equals to primary current. There is an additional current I2 dash and no load current. So addition of these two equals to total primary current. Now here primary current, this is I1, and this is I naught, and this is I2 dash, this is V1, and this is a fly, and these two are in phase. Now if you see this diagram, second diagram, this is for inductive load. Inductive load case, same thing, I naught plus I2 dash equals to I1. So but here this is only difference. Current lags voltage by some angle. So there is a resistive. And next, if it is a capacitive case, this current leads voltage by 90 degrees, some angle, that is capacitive case. So in this case, so this is wrong diagram, I think. In this case, so that I will draw first here this one. So first same thing here, this one, and this is E2, and this is I2, and this I2 is completely, this is I2 dash, and this is the I naught, and if you add this to one, I1, and this is the phi naught, and this one is the phi 1 dash, this one. So this is a V1, and this one is a phi, this is E2. So these are the three vector diagrams for resistive load, inductive load, and capacitive load. So now if you take one problem, first, transformer current for 4400 by 440 volts, a single phase transformer, 50 Hz, that value is 0.04 amperes, this one, and it consumes 80 watts at no load when supply is given to LV side and HV side is kept open. Calculate the power factor for no load condition, no load current, and iron loss component and magnetizing current. Power factor means cos phi. Cos phi can be calculated when power factor is given. What is the power factor value? First calculate, and iron loss equals to, and magnetizing IW, and this one IW or IC, and this one is a IM or I mu. These two are. Now here, first one, solution for this, what are the, so I naught is given, that equals to, I naught equals to 0.04 ampere, and W naught equals to 80 watts. And next, what, 50 H. Now here I naught equals to, and W naught equals to. Now here I naught equals to cos phi, you calculate this. V1 is given, that one is 4000, V1 equals to 4400. So W naught, V1, and I naught from this cos phi naught. So power factor is over 0.0454. This is the power factor. And next thing, IW equals to I naught cos phi. So you can substitute here this 0.044, and this one is a 0.04, and this one is core loss component or iron loss component of no load current, and I mu equals to IC, or this one is the I mu. I naught sin phi, that equals to 0.0356. And next, a 440 by 120 volt single phase transformer takes no load current of 6 amp and 0.3 lagging power factor. If secondary winding supplies a current of 30 amps at a power factor of 0.85 lagging, and determine the current taken by the primary winding. So I1 is, you need to calculate. So first one, so if you draw the graph here, so this is the lagging power factor. I2 lags this V2 or E2. This is the reference, and this is I0 and I2. This I1 you need to determine here, and this is a V1. Now here cos phi naught, so no load power factor 0.3, cos phi naught equals to 0.3. This phi naught equals to 72.4. This one is the angle between V1 and I0. So this is 72.4, and cos phi 2, this equals to 0.85, that equals to 31.79. This value equals to, this is angle between I2 dash and V1. So now here, if you know the K value, transformation ratio K value V2 by V1, that equals to 120 by 440, then that value equals to 3 by 11. So now here, if you know the I0 is 6 amp, but here to get this I2 dash, we need the K value. So now here I2 by N2, I2 equals to N1 I2 dash, that equals to here N2 by N1. So I2 dash equals to N2 by I2 dash equals to N2 by N1. So this equals to I2, sorry, that equals to I2, that equals to I2, that equals to K into I2, this formula, and a K equals to this one you can substitute here, and I2 equals to 100. So that equals to 27.27. This one is a 6 amp. And now the angle between this angle is 31.76 and this angle is 72.54. And what is the angle between this 72.54 minus 31.79? If you know this angle and if these two magnets, then you can calculate the I1. That one equals to, this one is 6 amp and this one is 27 point some change, and this one is the angle between, difference between these two. So now this one is a 40.75. So now here if two vectors summation equals to, so these two I2 square and I0 square, that 2 into I0 I2 dash, I0 I2 dash cos phi naught, this angle between these two is this one. If you substitute in this one is 27.27, this one is 6, and 2 into 6 into 27.7 into 4 cos of 40.75. So that value is 32.05 amperes. This one. So this primary current taken by primary winding is 32.05. I hope this concept is clear to you. No load condition and load condition for transformer, ideal transformer and practical transformer, and these two problems. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.